In the previous video, we have discussed what happens when two waves with the same frequency overlap in space. We have seen that you can have constructive or destructive interference depending on the relative phase difference between the two waves. In this video, we will look at what happens when two waves have equal amplitude but slightly different frequencies. And we will show that the resultant wave forms beats with a frequency equal to delta f. So again, when you have two waves that overlap, you can use the principle of superposition. And here, because the frequencies are different, we will have two different wavelengths and two different periods. And so we also have two different wave numbers, k1 and k2, and two different angular frequencies, omega1 and omega2. Now, to simplify, we can choose to consider what happens at the position x equals 0, right? And we know that at a different position, the signal will be the same, but it will simply be shifted. And we can also drop the minus signs because cosine theta is equal to cosine minus theta. And so we end up with a cosine omega 1t plus a cosine omega 2t. Now, at this point, you can already guess that we will use a trigonometric formula, right? And you're already familiar with my trigo slide that contains all of the formulas that you will ever need in this class. And so let's see, cosine omega 1t plus cosine omega 2t. This looks a lot like this cosine A plus cosine B formula, right? And that is 2 cosine A plus B over 2 times cosine A minus B over 2. So coming back to our situation, we have 2a cosine omega 1 plus omega 2 over 2t times cosine omega 1 minus omega 2 over 2t. So we have a product of two cosine functions, and one of them has the average angular frequency, and the other one has the difference of angular frequencies divided by 2. And if the two frequencies are almost equal, then delta omega will be small, so the second cosine function will have a slow frequency. Let's look at a graph of this function. You can see that the amplitude of the oscillations is given by plus or minus 2a times a slow frequency function, that is the red curve that you have on this graph, and it has the angular frequency of delta omega over 2 or a frequency of delta f over 2. Now, if you look at the red curve, you can see that over one wavelength, there are 2 beats. So there are 2 beats every full period. So that means that the frequency of beats is 2 times delta f over 2. And so the frequency of beats is equal to delta f. Now, here is an example with numbers. Let's say that you have 2 waves, one represented in blue with a frequency of 16 Hz. That means that over 1 second, there will be 16 periods, 16 oscillations. And another one represented in red that has a frequency of 18 Hz. So over 1 second, it will have 18 oscillations, so 2 more periods compared with the 16 Hz curve. So there will be times when the waves are in phase with each other, and so we will get a maximum amplitude, a constructive interference. And there will be times when the two waves are out of phase with each other, and this will produce destructive interference. And in this example, you see that we have 2 beats in 1 second, so the beat frequency is 2 Hz. And this is indeed equal to delta f. Usually, you can hear a beat frequency when the two waves have frequencies that differ by 6 or 7 Hz. And when the frequency difference is larger than 6 or 7 Hz, then we cannot hear the beats. And this sounds more like a consonance or a dissonance. Right? The beats are still there, but they are too fast for our ear to distinguish them. Now, real life example, for some small airplanes with 2 propellers, if the 2 propellers are not running at the same speed, then the pilot will be able to hear a beat frequency. Right? And so the propellers can be synchronized by making the beat frequency smaller and smaller. and this can be done just by listening, or it can be done electronically.